How you doing? Today we're going to look at the net change theorem, which has a lot of applications, but the first one I want to think about involves velocity and position functions. Now earlier we saw that the derivative of a position function was the velocity function, or just kind of more simply, the derivative of position is velocity. And then similarly, the antiderivative of velocity is position. So if we have velocity and we antidifferentiate, that should give us position. But now that we know the connection between antiderivatives and integrals, we can apply the fundamental theorem of calculus here to get something very interesting. If we take a look at the integral of a velocity function, say we know the velocity function between two times, t1 and t2, well, we know the antiderivative of velocity is the position function, and so this is going to be the position at time t sub 2 minus the position at time t sub 1, because, again, position is the antiderivative of velocity. This is what we get when we apply the fundamental theorem of calculus part 2 to a velocity function, so long as it is a continuous function on the given interval. And we call this quantity on the right the net change, which means basically the change in position from the starting time to the ending time, from t sub 1 to t sub 2. It doesn't tell us how far we've traveled. If you went back and forth 30 times along some sort of a line segment, it wouldn't get the total distance that you had traveled. It would give you the difference in position between where you ended up and where you started. That's what net change is. It's just looking at the end result and the starting result and how far apart they are. And this is effectively the net change theorem. It says that the integral of a rate of change is the net change. Now what that means is if we're integrating a function that is a rate of change, and we know velocity is the rate of change of position, then the answer we get when we take that definite integral is the net change of that function, meaning the difference in values of the starting and ending positions. Now there are several different ways that we could apply this to different types of functions, and I want to go through a short list. First of all, we've seen the integral of velocity gives us the net change in position, but there's a few others. So we've got a few more here. If we look at this first one, if capital V of t is the volume in a reservoir at time t, then its derivative, V prime of t, is the rate at which water is flowing into the reservoir at time t. That's the rate of change of the water. And we might know the rate of change because we know how fast the water's flowing in via some sort of a pipe or something like that. If we know that rate of change, we can integrate over a time period, and that will give us the net change in volume. Basically, the difference in the volume at the end versus the volume at the beginning of that time period. So that's one way that we could integrate a rate of change and end up with net change in the end. The next example comes from chemistry. If bracket C of t represents the concentration of the product of a chemical reaction of time t, should be at time t, I believe, then the rate of the reaction is bracket C prime of t, and thus if we integrate the rate of the reaction over a time period, we get the net change in that concentration. Now, we're not going to do an example problem like this because we don't know what most of that even means, like actually, as far as how you're measuring it and how you work with it. And we haven't even seen this notation before. So this is not an example that we're going to actually get our hands on, more just an explanation of where you might see this in another field. The next situation where we might see the net change theorem is population growth. If the rate of growth of a population is dn over dt, then the net change of the population is given by the integral from t sub 1 to t sub 2 of dn over dt dt. And that is going to give us the net change in population. So it gives us the difference in population at the end point and the starting point. And we will have an example of one of those. There are other examples in your textbook and online, but again, these are often so involved that you need to know a little bit about whatever field they come from before getting your hands dirty. So it's not necessary for, I don't want to spend time giving you a long list of examples that we're never going to look at. The important thing to understand is that there's a lot of applications here, and the integral of the rate of change is the net change. That is effectively what the net change theorem means. There is one more example I'm going to give you, and we're going to look at an actual problem involving this, and it ends up being a little bit trickier. You might even already realize there's some absolute value symbols here. This example, or this category of examples, says if v of t is the velocity of an object at time t, so v of t is the velocity function, then to find the total distance traveled. Now that's not the distance between the starting point and the ending point, but that's actually how far it's moved. If someone was pacing back and forth over and over again, and we had this as a velocity function, then we might want to know actually how far did they travel, not just what's the distance between their starting point and ending point. If we want to know the total distance traveled, we integrate over speed. And the difference between speed and velocity is that velocity has a direction inherent in it. We only usually look at these problems moving forward and backward. So the directions are the positive direction and the negative direction. But speed ignores direction, and it's just how fast you're going in whatever direction you're going at a given time. And if we integrate over speed, which is the absolute value of velocity in these situations, then you end up getting the total distance traveled. We're going to do an example of this in the next video, but I just want to tell you in advance, this ends up being complicated because we don't know how to integrate a function that has absolute values around it. We don't have a rule for that. So what we're going to have to do is we're going to have to look at when our function is positive and when it's negative. And when it's positive, the function is equal to its absolute value. So whatever that subinterval is, we're just going to integrate normally. But then whenever this is negative, we need to take the opposite of that function and integrate to make it a positive function. Because when we take the absolute value of something that's negative, we have to take the opposite to make it positive. So that's what we're looking ahead to. And it sometimes takes students a moment to wrap their heads around it, but that's why I'm telling you a little bit before we watch the video what is to come.